Well, hello there, ladies and gentlemen. Let's wrap up the beginning part of this transformation section by talking about some translations. So here we go. Let's go ahead and take a moment and set up our page. As you know, you need to. Please don't forget about this information. It's something that's just going to be a good habit to get into by the time you get to college. We are talking about translations. And in particular, the essential question we're talking about is how do you prove a point has been transformed by a translation? Now, translations are the ones we probably went through the fastest. Like we took the, let's say, least time developing the ideas because you guys already have a good framework for addressing and talking about these transformations. So a translation has some really nice casual way to describe it. Things like slide or move or uh, I think I said slide already, didn't I? So like slide or move or push down a line, like that's what it means to translate. Like kicking a chair across the room, you're moving its position, but you're not changing its orientation, which is a really big thing about translations. So it should be oriented in the same way as when it started. In other words, no rotation, no reflection, nothing like that. Anyway, so jump into the notes. So let's talk about our pretty much at this point standard first section. What can I say? Let's write in black. Okay. So let's talk about some words that you absolutely need to know so you can talk about translations really well. That first word that we need to talk about is parallel and what it means to be parallel. Well, parallel lines, and if you want to kind of think of it in terms like an example, parallel lines, of course, are running in the same direction and they never touch. But what you need to kind of drill down to is why they never touch. So if I have these two lines, let's call them like line L and line M. L is parallel to M, certainly. Not just because they're marked, because I'm intending to show that these two actually will never intersect in any way. So if you're thinking about why they never intersect, it's because they're always the same distance. They're always equidistant. So parallel is defined I shouldn't say defined, but I should say applies to lines that are always equidistant from one another. And this applies, of course, to planes as well. Points aren't typically ever parallel. Like it's not just it's a dimension mismatch. Like it's not something you can talk about in terms of lines. But they, of course, never touch. And again, the reason they never touch is because they're always equidistant. I didn't even finish the word. Distant. Okay. So now when you're talking about this term equidistant, that kind of gives you a sense of what it means. If two things are equidistant, that means they're always the same distance from one another. A way to break down this word is in kind of two parts. You have equa, which is like equal, and then distance, which is like distance. So the term equidistance means that they are same distance away. Okay? And what they are could be a lot of things. Points can be equidistant, so can lines or planes or even solids. So when you're talking about equidistance, you're talking about equidistant away from one another. Okay. Now let's talk about vector. Vector we talked about a little in class, and this is something that will come up in physics as well. But vector is nothing more than a combination of distance and direction. Okay. Another way to say that would be like magnitude and direction, which is something you probably experience more in physics. This term magnitude, it means the same thing as distance. Okay. Now, the way these, of course, play into this idea of translation, that if I have a point, let's call it A, and I'm translating to a new point, let's call it A prime. Well, the way to describe that that translation is to tell me a vector. So this right here becomes our vector. Okay? The vector, excuse me, the vector itself. Oh yeah, no, ooh bad. Never mind. Cardinals are down. End of the sixth. It's okay. It's okay. We're up 3-1. We can drop a game if we need to. But anyway, if you're going to describe a translation, you always have to involve a vector because a vector tells you where to go. So if I take this A and translate along this vector that gives us a distance and direction, I should end up at A prime. That's the basis of translations. Like that's the whole thing. So if you're thinking about what question off to the left-hand side is going to define these notes really, really well, hopefully you come to the conclusion that these are the key terms. So the question might be something along the lines of, what are the key terms for like translations. And again, it's not important that you copy this down verbatim. It's important that you understand that what we're showing off to the left are the important things you have to know and be able to use when talking about translation. So it's almost impossible to describe a translation well without using at least one of these words. The most important word, I think, being vector. I think parallel and equidistant help describe the vectors after the fact, but vector is certainly the key feature here. Okay, so let's drop down. Let's talk about like these guys right here. So if you're talking about these two things, the algebraic rule and the general rule, I would say that these two have a part to play in the description of a vector. So let's first jump into the notes, and make my statement like make a little more sense. Excuse me, I'm stumbling all over the place. So an algebraic rule is usually expressed like this. Whoa. Man, you know what? Let me just chart over. That just got all sorts of messed up. So we have xy being our pre-image point is going to be translated to our new point x plus a and y plus b. Okay. So if you're kind of tracking these parts, this piece right here represents the pre-image. And this guy right here represents the image. In other words, we're taking x, y, and then we're changing it in some way to get our new point. So just like the examples before, this a and this b actually are going to define the vector. Okay? These are going to give us that distance and direction that we were searching for. So what I mean is something like this. So if I have this pre-image, and let's call it like 4, 3, and I take it to, I'm just going to kick it all the way over here. If I take it to this new image vector and call it like 8, 2, well, if you think about the transformation that has to take place in the middle, we took our x value, 4, and we added 4 to it. And then we took our y value, which in this case was 3, and we subtracted 1 from it. So this, the adding of 4 and then the subtraction of 1 actually give us the distance and the direction, hence the vector of our movement. Here's what I mean, and we can probably squeeze this in right here. If you think about what this graph would look like, we started in with 4, 3 as our point A, and then we're translating up to, well, not just up, but up and over to the to a, 2. So 8 and then 2 should be right here to 8 prime. So the reason why this plus 4 minus 1 describes a vector, because it actually is a valid way to describe how to go from A to A prime. So in other words, let's say I'm sitting here at A. This is me. Okay, and I want to get to A prime. Well, how would you tell me to get there? Well, one way you could tell me to get there is like down 1 and over 4. Which, if you look, is precisely what our vector is saying to do. We have down 1, which is right here, and then over 4, which is that right there. So again, so to shorten it, we could take a more direct path. Okay? So instead of saying going down 1 and then over 4, we could just say, well, let's travel straight along this line. It amounts to the same thing because it ends up in the same place. So this would be the vector of travel from A to A prime, which can be expressed 2 different ways, as a movement of x plus 4, y minus 1. It can also be described by the vector 4, negative 1. And again, notice that vector notation is slightly different. It has those pointed brackets, and it just has the movement overall of x and y. So that kind of thinking actually leads us into more of a general rule. So if I want to execute a translation, I can say T is my translation. The important piece I have to mention is my vector. I have to include my pre-image, and that's going to take me to my image. Okay. So for like the algebraic rule described above, we'll have this translation of 4, negative 1. of the point 4, comma 3, and that's going to take us to the point 8, comma 2. Okay? So the advantage of using a general rule is that I don't necessarily have to also just use points and like coordinate points. I can also use this to describe a general translation. So for example, okay, if I have this triangle, let's call it triangle ABC, and I want to translate it to this new triangle DEF, I can accomplish that two ways, one being the algebraic way, which isn't really suitable here because I don't have a grid, but I can also identify a vector of translation. Now, if this were on a grid, that would be the direct path it would take. So for this one that I have mapped out on the left, I can just write a general rule for this. So T along the vector of, of A to D, translated vector A to D, of triangle ABC is taken to triangle DEF. Okay. So just be aware there's ways we can apply that general rule as well. Now this also gives us a sense of what we should make as far, or what should be there as far as the construction. So if we kind of re-examine the example we just had, we have triangle A, we have triangle B, and we have triangle C. And we want to translate it to this new triangle. Again, let's just go with DEF. And I know it's not perfectly to scale, guys, just go with it. The question remains, like, what do I actually have to, let me see if I can do this. Yeah, it's pretty close. Okay, so if I want to translate it, I'm just taking this and moving it, I'm sliding it. So the question is, well, what do I have to actually construct? Whoa, partner. What do I actually have to construct to confirm this happened? Well, this goes back to this idea of vectors, which is just a direction, the magnitude of travel. If A has to travel to D, doesn't it stand to reason that all points have to travel in a similar manner? What I mean is this. If I'm defining this to be my vector of travel from A to D, and I want to keep these shapes to be absolute same, I would argue then, no, you let go. Stop it. Okay, so if I had to travel from A to D, I would argue then every single point has to travel in the exact same manner. I have to travel from B to E and C to F the same way. In fact, if you kind of look at them sliding these along the perimeter of the triangle, every single point has to travel the exact same way. Like, I know it's not perfect, but this isn't a perfect drawing. If I could make this perfectly to scale, like, you'd see these points completely line up. So if that is a direction of travel that has to be mimicked by all others, if I look at all these points of travel, these vectors of travel side by side, I should make a general observation that these vectors are indeed going to be parallel. This isn't a huge surprise, or at least it shouldn't be. And again, I know my drawing's not perfect. Again, just go with it. But if these weren't parallel, then we'd violate a lot of rules that we know have to be true about translations. For example, and this is a non-example, don't write this down, just please watch. If I had this triangle that I want to translate, so I want to take this and let's say I want to move it to here. If I didn't follow the parallel rule, I would be, parallel vector rule I should say, I would be in real trouble. And here's what I mean. If I said I want to travel using this vector, and then instead of simply copying and pasting, ensuring that it's the same one, get in there, paste, okay? Let's say I didn't want to follow that anymore. In fact, I wanted to do, on this particular one, I wanted to change the direction of travel. Let's keep the distance the same, but just change the distance of travel. Okay. Well, what would happen? I would no longer have this triangle as a result. I'd have something else because I have to go to the end of the vectors. Again, let's say I had, well, this is a vector I intended to travel on, but instead I decided I wanted to take that vector and actually lengthen it and go out to here. Same direction, still parallel to my original vector, but now somewhere else. Well, we saw this with the rotations. If you don't keep everything the same, the resulting triangle can't be a translation of the original because in this case it's bigger. It's also been inverted. A lot of things have happened to it. So in the end, what you have to construct has to be parallel vectors, which amounts to constructing, say, parallel line segments. The reason I'm using vectors is because vectors include both a direction, which makes them parallel, and a distance, which makes them the same length. So you could really say two different things. If you want to construct something that can confirm a translation, you're going to have to construct either one, congruent vectors, same size vectors, or two segments that are parallel and congruent. Which again amounts to the same thing, and I forgot I left a word out of there. I should have said same vectors. Okay? And of course, when I say you have to construct these things, these will always be from pre-image to image. Okay? So this is like the non-example. And this is like the example. So if I follow this rule of keeping same vectors, if I'm constructing same vectors, or in the case where, again, it amounts to the same thing, but constructing three segments of the same length, then I should have a correct vector, or I'm sorry, correct translation. Again, I know my picture's not perfect, but you can see if I would have copy and pasted correctly, it would have worked out great. On this one, I'm constructing vectors that are of different sizes, and one that's not even parallel to the rest. And you can see my resulting triangle is not even a translation. In fact, it's not even the same kind of shape. So in the end, what you really have to construct to confirm a translation are the same vectors or segments that are parallel congruent, which would end up being the same vectors. Okay? So if we're going to fill in some questions here on the side to kind of help guide our notes, well, over here we're talking about the rules of how you represent or describe a translation, so we can record that as a question. Okay, so we have two different versions of that. And then down here is actually the general construction. So what do you have to construct to prove? Okay, so those are the notes you need to engage the next part. Uh-oh, that is not good. We can still come back. So these are notes that you need to engage in the next part of our discussion, next part of class. We need these notes about translations. So I invite you guys to go ahead and make sure you have these down. And just like before, after you watch the video, I need you guys to do the summary. Now, guys, if you're not doing your Cornell Notes summary, you are not using Cornell Notes effectively. In fact, I think you're reducing the effectiveness of Cornell Notes by at least 50%. This is the most difficult part, but this is also the part that is the most applicable directly to what we're doing in class. You have to pick out the most important things. Okay? Then you have to use those things in the actual writing that you do. If you notice, a lot of my tests are writing. This is your opportunity to practice the writing that's necessary. If you want to answer my test questions well, you have to be able to do this type of thing extremely, extremely well. Pick out the important parts, right? Use those important parts in your explanation. You gotta practice, guys. So once you're done with that, please repost an Edmodo as a reply to this video. I'd greatly appreciate that. So would everybody else, so they have a chance to kind of bounce their ideas and compare them to your own. I appreciate all that you guys are doing. Thank you for working hard, and I will see you guys later.